Okay, welcome to this third part of our technical briefing in Bayesian Data Analysis for Software Engineering. My name is Robert Feldt, and I will talk in this third part about using Bayesian Data Analysis in software engineering. So a little bit take it back to more higher level of what this can mean for our scientific field and for practice in practical software engineers. So what is the bigger picture? Well, in part one, Carlo told you about the motivation for using Bayesian data analysis. And in the second part, Richard showcased some of the steps involved in a typical Bayesian analysis. And we need both of these, of course, if we're going to use this. But we think that we also need more of a guideline, kind of a workflow, a process for how are we going to use these steps and statistical tools, analytical tools on our software engineering data. And of course, I don't have a lot of time in this third part, so I will try to do it fairly briefly. And I cannot give you so many examples because of that. But I think one important thing that I will talk about is how can we use the output when we use this kind of a workflow. So what is the workflow and how can we use this output? And I will simplify and only mention two types of output. And the first one is a scientific kind of benefit or output from this. And that is that we think it will be easier with a Bayesian framework and ways of working to create chains of evidence between several studies in software engineering. And the idea is that my posterior, the output of my Bayesian data analysis from the analysis of the data I have gathered in my study, can then become and give input to a prior for a follow-up study or for someone else that needs part of that are asking a related question and need some information that our posterior can provide. So it's not that we cannot do this with frequentist other types of statistics. It's more that it's a very natural part of a Bayesian data analytical framework because you need to consider your prior. So then it makes perfect sense to, when constructing that prior, to take in information and posteriors from previous work. Another output is more practical, so sort of an engineering output from this is that we can use our posterior, so the outcome of our analysis, and do practical simulation. So simulation of what would happen if we were in this type of situation. And by combining these type of simulations with often cost estimates and so on from practitioners, we can discuss with them and give evidence and predict practical implications. So we can consider in a practical way the significance of our results. And this is a big benefit. And by using the posterior, we will have the uncertainty from our study still in there, and that will propagate into our analysis of the practical implications. So, to summarize this, we will have some kind of prior information we'll set up, and we will have a workflow that leads in the end to some posterior from the model we have chosen, and then we can do practical simulations and consider the practical significance. Okay, this is a complex picture from a book that is being written by some statisticians. Gelman, very famous one in Bayesian data analysis. And they are writing a book on Bayesian workflow. So of course, they consider many more aspects than I will go through here. And probably they consider more than you will typically need when you analyze the data in your study. But this is to show that these workflows and processes and guidelines are not yet complete. They are being developed now in statistics, and we can, of course, follow this and simplify it and adapt it to our software engineering context. And in fact, there is a current paper by Carlo, Richard, and myself, which is on arXiv, which tries to do this. It does a simplified workflow for software engineering and has an example case. And you can go to archive later and study this in more detail. And hopefully it will be published in the future. It's currently under submission. So we will not go into the full workflow or every aspect of this, but let's talk about the simplified version that we present in this archive manuscript. And a fundamental idea here is that we will do incremental modeling. So we will not simply do one model, run that, and be done with it. We will rather build our model in steps. So in the end, we will have actually several models that have different levels of granularity or resolution that we can then compare. And why do we do this? Why do we build in increments? Well, it's unlikely that we can find the right model or resolution directly. So, there are many trade-offs in modeling, and it's very natural in a Bayesian data analytical framework to consider different models and to see what are the benefits of the more detailed models compared to other trade-offs we might need to do. So what we will do is have in increments several models, and we will, based on what we learned from the ith one, the previous one, which model should we try next? How should we vary the current model we tried in the next step? That is what we're going to do in increments. So this for a software engineer is quite natural. So it's more kind of an agile way of working where we explore and adapt, guided by the previous results and what we have learned so far, right? So we reason about, we reflect about what we've seen, and then we explore and take the next step. There are two main practical starting points. One is to start from a very simple model and make it more and more complex in steps. So we start small and we build up. Another way is to start from some known model or even a frequentist model, and then we explore if we need to simplify it or maybe make it more complex. Because in Bayesian data analysis, because it's not a toolbox of pre-made models or statistical tests, we can actually we have a lot more flexibility in how we build the model. So we can vary more aspects of our models since it's a framework. It's not a toolbox of pre-made statistical tests or models. A more rare starting point can be to start from a large and complex model and then simplify that in steps. So, how does this incremental build, compare, and analyze steps work? Well, we will start with a first model, the initial one called M1 in this picture, and we will consider three things for every model we build. We will consider first, is it plausible? Then, can we work with it? Can we compute with it, even as it's formulated without considering the data? And then adequate. When we run it with the empirical data we have collected, can it capture the characteristic of that empirical data? So can it sort of summarize and be a good representation of the data we've actually seen? So these three steps go from plausible, focusing on the prior, workable, focusing on doing computations with our model, and adequate, focusing on does it actually reflect the empirical data that we have seen and collected in a good way. And then, based on what we learn in the adequate step, or maybe in even analyzing the model, number one, we can then incrementally add some aspect or change some aspect of model 1 to have model 2, and then we will go through the steps again. And in the end, we can compare what the models tell us about our research question, and we can analyze which model do we prefer and what does it tell us about our original research questions. And we have then our results summarized in our posterior. So, looking at the first step, plausible. The focus is the prior that we set plus the model that we have formulated, is that consistent even with basic domain knowledge that we have or end users have or the people we are investigating or helping? So we are not using our actually collected empirical data here. We're looking at our prior and running that together with our model to see what would it mean. Is the prior consistent, or are the results of the model consistent with what we already know before looking at our data? So we do something called prior predictive simulations, which is we run the priors through the generative model, the statistical model, and we look at what does this mean and is it realistic. So if we look at the example that Richard alluded to in his part 2, we looked at the distribution of project effort. Okay, so what can we say about the prior? So what are the steps in a typical workflow we can consider? The first is we can think about, when we think about the prior, is are there any physical or logical limits that we need to respect? So probably it's physically impossible to have software projects that are that take less time than 0, right? So negative project length is impossible, physically impossible. There are also logical limits. We cannot have projects that are several 100,000 years because Homo sapiens haven't existed, and we assume that most developers are from the species Homo sapiens, right? We can also look, when we consider our prior, on commonsensical things. So very short software projects, say that only live for a few hours, doesn't really align with our common sense knowledge about software projects. And very long projects, say that take several decades or centuries, is also very kind of strange from a commonsensical perspective. And we can then be even more specific and looking at the prior research when we set up our prior. So this is a way we can connect and build chains of evidence. So we can actually use results from previous studies here to calibrate and make our prior more realistic and in line with what we already know. So maybe software projects are typically on the order of a few weeks or up to a few years maybe. But depends on what kind of study we are doing and what we consider to be a project. Maybe maintenance can make this into something even longer. In the plausible step, we can also consider modeling factors or variables. So, for example, if our model has kind of a linear structure, so we have some kind of coefficient in there that scales with programming language and so on, it seems unlikely that that there will be a factor of maybe 1,000 difference in these coefficients. So it seems counter to our previous domain knowledge that one programming language would make for 1,000 times more productive project, for example. So this is about not looking at our empirical data, considering the prior and the model together and see, is this, when we run them together, is this a plausible result in line with what we know? Second step, when considering one model, is can we kind of compute with it? So this is kind of a black art, so I will not give you much details about that. But what I can say is that a lot of your time doing Bayesian data analysis will be spent in this step. And, in some sense, it is a good thing that we have these computational tools with which we can investigate what happens as we do inference with our model. Because the model is kind of speaking to us, and it is kind of a folklore theorem in Bayesian data analysis that we should listen to this model. And if there are computational problems, this can also indicate there are problems in the way we conceptualize and build our model itself, logically, so to speak. So for example, if the training or inference takes days or weeks, well, probably there is some problem with the complexity of your model, so you will need to simplify. And there are many tricks here, and of course I cannot go into all the details here. If the computations diverge, you might need to reparameterize your model variables. And of course, there are lots of guidelines on doing this. But for this step, we need to rely more on the statisticians, because this is about the actual workings of the statistical tools and software that we use in this. For example, high uncertainty, maybe this would come in the next step, but you can consider it here too. Well, if the uncertainty is very high in the output, you need more data or adding other prior information. A caveat with this step is that better tools continuously make more complex models tractable. So this is kind of a moving target here. And, maybe in a year's time, you can run the model that you actually want to run. Automation will also help here. So there's a lot of research going on in statistics and machine learning that will be helpful here, so that they can do reparameterization, for example, automatically, or maybe investigate changes to your model or computation to make it more feasible. But in the end, this step is a little bit of a black art. So that it's very hard for anyone to give you lots of detailed advice for how to do this. You will have to follow the books and writings of the statisticians in this and sort of learn as you go along. The adequate step is about actually running our model with our empirical data and may do the inference. So I will not say so much about it, but the general question is, when we run our actual collected data through this model, can the model posterior, the output, actually, is that in line with the data we have seen, right? That should be the case, because we are using the data plus the prior, running that and setting up the parameters of our model to fit the reality or fit the actual data in a good way. But of course, there can be computational problems, other problems in modeling, which makes it so that this doesn't actually happen. And this step is about ensuring that it happens and leads to a good representation of the actual data you have seen. So are there some parts of the data that are missed by the model, for example? So what you will do here in practice is these posterior predictive checks that Richard mentions. So it is very similar to prior predictive checks, but when you did prior predictive checks in the plausible step, you weren't using your actual data. And here you're actually using the data you have collected and running that through the model. So that's the difference. But in the actual comparisons you do on the output side, that it will be similar to what you did in the plausible step. And then when you go through these 3 steps for one model and later for another model, and then at some point you want to compare these models to see, should we have a third model, or which one of these do we prefer, and so on. So basically this comes down to some kind of simplicity versus accuracy or fittingness trade-off. And it also relates to the bias and variance trade-off you've heard about in machine learning probably. And the good thing here is that there are many good and recent research to help you out here. So there are good metrics and there are good tools for doing model comparison in BDA. So this will be relatively simpler. It's more about learning to use existing tools rather than the computational checks in the second step that we discussed that are difficult to do, even for the experts in some sense. But it's important to think here that it's not only about accuracy or the fit, right? So just as in other elements of modeling, we have to consider the scientific cost of having a more complex model. So, doing the trade-off here in comparison can partly be done based on automated tools and automated metrics. But we also think that in software engineering, you should consider the scientific cost. So maybe one model is actually better from a simplicity versus accuracy trade-off, but what is the scientific cost of having a more complex model? I mean, in some sense, we can always refine a model and it can be, but at some point we want to stop and have a good capturing the main factors in what's happening in reality. So this is important to consider. And of course, there are also practical costs. I mean, my experience working with industrial practitioners is that a larger model will be harder to explain, harder to understand, so it's less likely to be used. So, here you can, in doing these model comparisons, it's not only about using these statistical metrics to compare models. You also should consider the practical and scientific costs. Okay, and then when we've done model comparison and we have incrementally developed a few different models, we should analyze what do we actually learn from the posterior in the end, from the one model that we have preferred and selected. So what does our model say about our original research questions? So what you typically do here is create some kind of plots or quantitative summaries of the posterior. And you select the ones that relate to your research questions. So you will be comparing medians, you will be looking at credibility intervals, you will be plotting distributions to see what are the key factors and are they sort of giving large effects or not. So you can then, as Richard mentioned, you can calculate probabilities and comparing different languages or situations in the data he considered, for example. Okay, and then practical significance. So this is we think will be one of the benefits to us as software engineers in using these technologies. So it becomes easier to see what does the outcome of our analysis, what does it really mean? What does it really imply? And the reason is that the posterior distribution that we get as the output includes the uncertainty of our data run through this model. So we can then use this posterior to simulate specific situations or scenarios, and then we can answer specific practical questions in the domain. So if we consider the example Richard showed, where programming language, for example, or let's say we consider an example where programming language is connected to project effort. So which language should we choose in this new project? So then we have something we know about the new project, and we can then vary the variable of language and see what would be the interval or what would the distribution of project efforts look like. So what we can also consider a situation where we are actually using one language, what kind of gains can we expect of switching from one language to another? And if we also have some kind of cost estimates or actual data on the costs involved, we can then combine the posterior simulations with cost effectiveness cost information and get intervals of the actual cost, return of investment, for example. But this last step will typically need us to solicit or collect information from the experts in the domain. But in some sense, we have found that often engineers and practitioners already can do these kind of ballpark estimation, back of the envelope kind of estimations of costs, and then we can run with that. If you want to see, I don't have time, of course, to go into details here. So there is a paper on practical significance that shows this in more detail. And just to show you one example, so we analyze we replicated the analysis of an old data set that compared traditional sort of script-based test cases with exploratory testing. And one scientific outcome, which would be similar to running a frequentist analysis on this data, would be to look at how important are different factors. So for example, in this experiment, they collected data about the experience of the developer or tester when using the different techniques of exploratory testing or scripted test cases. And then we can see here a scientific outcome of a summary of the posterior would be that the factor for experience has a lower effect because it's closer to zero here. You see the distribution on top compared to the choice between exploratory testing and test scripts, which is technique factor here. because that one is further away from zero. And you can see it in the paper, but then we run simulations of different situations. So like we can simulate then if we are creating a new project, should we then have developers of having low experience or high experience? Should we select exploratory testing or test cases, these traditional scripts? Or we can even run simulations of combinations like exploratory and low experience compared to exploratory and high. And we can get out the estimates in the concrete language. So here it is, the expected number of faults found or failures found using these different scenarios. And then we show in this paper that by having cost estimates, you can then get actually the distribution of utility. So connecting this cost with the posterior, we can actually estimate what is the cost effectiveness, the return of investment of using exploratory testing on top here compared to test case testing. And you see here in this case the utility was quite high going for exploratory testing. Yes, so simulations plus some estimated cost can give us actually practical implications and then help us analyze practical significance for industry in general or for specific scenarios for one company, for example. So very useful, we think. So last slide, the scientific output of using BDA in software engineering can be, we think, it will be easier to build chains of evidence. So basically the sort of idealistic view is that I have my prior, I run this workflow, and in the end I get a posterior that can help me answer my questions, but this posterior can then help and become input to the prior in a next study, and so on. So we can build like ladders of studies that more directly build on each other. Of course, this is idealistic, because in practice we cannot go directly and use a posterior as a prior in the next step. Often this goes through some kind of knowledge created, and then we can sort of calibrate our prior in the next one. Okay, this was super quick and I couldn't cover a lot of ground that I wanted to cover, but at least we hope that this gives you a flavor and encourages you to explore this some more. So thank you for listening, and this concludes our technical briefing. Thank you.